Continuing our discussion of Linux stack buffer overflows, in previous videos, we determined that it's rather difficult to exploit a stack buffer overflow in a standard Linux application that has the stack protector enabled, which they all will by default. So, what I've done is I've added to my program an extra function. And first, I defined a function pointer type. If you're not familiar with function pointers, there's something that very commonly used in C and also to some extent C++, although C++ typically it's done internally, and in C it's done explicitly. And what this is, I've defined a function pointer for a function that returns void, and the name of this type def is funcptr, and then it accepts one parameter, a character string. Right after that, notice that I've defined other function, which has this exact same signature. And what am I going to do with other function? Other function will use printf to print out the parameter. In function, I've added a new parameter, func pointer type, and I'm going to call it fptr. Here, I have the stir copy function as I did before. And after I call stir copy, now I'm going to invoke this function, and this is the syntax for that. You take the function pointer variable name, put an asterisk in front of it, put all of that in parentheses. Here is the function call, if you will. And then in parentheses, you pass it parameters as you normally would. In this case, I'm going to pass it param. In my main method, if you look at where I'm calling function, I'm giving it the address of other function. That's what the ampersand before other function does. So if I go over here to my command prompt, I can compile this using GCC. And again, I will give it debugging information. My program is called Linux stack fptr.c, and I will output it to fptr. Notice it gives me a small warning. Incidentally, if I had not used printf correctly with a format string, I would have gotten an additional warning. If I run my program, fptr, and I give it a string that should be legal, everything is fine. And if I give it a slightly longer string, it's going to become unhappy. And there we go. It's detected my attempts to smash the stack, and it's aborted. All right, so the question becomes, could I overwrite the function pointer, perhaps call a different function with the same kind of a signature, takes the same number of parameters, and pass control of my program to that method? And the answer is yes. If I'm careful about it, I could actually go about doing such a thing. How would you investigate that? Step one would be discover a vulnerability in a program, a Linux program that has a stack protector, but is also using function pointers, which might be passed as parameters. If I again load this program up in GDB, I can list my program. And here you can see that it's gotten a little bit bigger, but it's mostly the same. I will set a breakpoint. In this case, I'm going to set a breakpoint on line 15, run my program. I've hit my breakpoint. I need to go a little bit further to get my values that I'm looking for. So I'm going to go ahead and step and notice my stir copy. And now I'm out of it. I can examine my stack once again. And now I see my parameter. Well, what else do I see? I see some addresses. What I want to do if I was going to try to chase down a possible vulnerability, again, you have to be careful because sometimes you'll find something and it's not easily exploitable. We'll see that is the case often when we look at heap overflows next. But sometimes you just cannot find something that you can exploit, or at least not easily. And then you have to get creative. Sometimes it just doesn't work out. That's the way it is. But here, if I look at my stack and I say, where am I storing this function pointer? What is that address? Once again, have a look at functions So I have a couple of different functions that are being defined, and I also can look at my program. So if I look at my program, if I print out my function, if I want to examine the address for my function, such as other function, here I have my address. I could print it out a different way as one nice big number, but I can look and I can find my function and I can find my function pointer that points to that function. I can look at function. I can look at the scope of it, and you'll see that I have variables that have been set up. And I can use some of those variables to figure out where I'm going to find a potential vulnerability. I can also disassemble this function, which will tell me where in memory or in my virtual memory space I can find that function. So there are a couple of different things that I can do in order to track that down a little better. So I guess the moral to this video is that it's hard in Linux to take a stack buffer overflow and turn it into anything useful. But there are a couple of cases where you can do that. If you have a function pointer that's being passed in as an argument that can be somehow overwritten, if you just plain get lucky and it happens higher in memory than some other parameter based on how things get rearranged, you might be able to overwrite that. Also, if you are encountering C++ programs, you should be aware that C++ classes implicitly have function pointers that point to the class and its methods that might be out there and might be exploitable as well. That's all for this video and our introduction to Linux stack buffer overflows and attempting to get exploitable vulnerabilities from them.